All right, hello and welcome to my presentation. I already said to the sound mixer guy that I feel a little bit like Britney Spears up here, so I'm really excited to be here with you listening to my talk. So I'm a PhD student at the University of Göttingen, which is a small and very beautiful student town in the middle of Germany. And I will be talking about a package which has recently gone through a name change. It was called bamlss.vis, which is why it still says that on your folders. But it was recently changed to distract.vis for reasons I will discuss further. And this is about interactively visualizing distributional regression models. So let's get started to get everyone on the same page. What is actually distributional regression? So let's say we have a variable y, which has a parametric distribution called d, and this parametric distribution has k parameters. And with distribution regression, what we do is we model every parameter theta I using a potentially different set of predictors. So we might be interested in some different parameter, and we can actually, with distribution regression, use different subsets of variables for different parameters. Furthermore, we can use all the effects that you might know from the generalized additive models or from the GLM framework, which means that we can use different forms, like, say, nonlinear terms, spatial terms, random effects, or just general linear terms. And also those parameters are connected to the predictors using link functions that uphold the support of the parameter. Okay, so you might know this from GLM. For example, the logistic model, it uses the logistic link function to obtain parameter estimates for pi, and this works for all range of different parameters. And essentially, this allows us to have extremely flexible model equations. Okay, so let's look at that long equation here for a moment. So we have theta L around here that uses some link function here, and then we have some predictors over here that actually are used to model this parameter. So maybe why do you actually need distribution regression? So let's say you're interested in modeling parameters beyond the mean. So this could be, for example, an income distribution, and let's have a look at this graph right here. And this graph shows different income distributions, so kernel density estimates for income distributions, depending on the education of the person. I mean, you can see that it starts at 0 because we usually don't have negative income, and we now have different distributions around here, or different kernel density estimates. And the takeaway from this is that you can see that the distribution not only differences in the location, which means that it doesn't only vary around the x-axis, but it actually also is different in scale, which means that we have a different variance, for example, for higher educational people, and for lower educational people we have a shorter variance. Which means that you might have different parameters that you want to model with different variables. So you've now come to the realization that you need this. What can you use to estimate those models? And there are like two different model classes that you can use. The first one are the generalized additive models for location, scale, and shape. It's a real tongue breaker by Rigby and Stanislaus, which introduced them in 2001, and there's an R package around. And now we recently also got the Bayesian additive models for location, scale, and shape, which take care of the Bayesian statistical side of that, and both have R implementations called bamlss and gamlss respectively, and my work builds on those packages. What are the differences? Well, the first one is a frequentist framework. We have a backfitted maximum likelihood estimation. The second one is a Bayesian framework, so we have posterior maximization and MCMC sampling. And we also can use multivariate distributions in the bamlss framework, and we can use structured additive effects in the bamlss framework as well. So you have a little bit more variety in what you can use to model your parameters. So just to give you an indication how these packages have been downloaded over time, since 2013, the downloads of those two packages have actually risen. I mean, I can only show you that for the gamlss package because the bamlss package is pretty recent. There's not the best indication here, but just trust me, those models are getting picked up over time. Yeah, so let's go to the motivation for my package that I wrote, District.vis. Let's talk about the motivation for that. So I already talked to you about distributional regression, which means that we model every parameter using different sets of predictors. And the problem is that in many cases, those distributional parameters, theta, do not directly equate to the first two moments, which are what most researchers are actually interested in, right? And so it's hard to know the influence of covariates on the moments because we have a link function that transforms the effects. We have transformed effects which are for the parameters, which are not directly the moments. And also non-parametric effects are on their own, even if we didn't have the first two problems, are on their own often hard to interpret, right? So let me give you a more thorough example. Let's consider the log normal distribution, which has two parameters, the mu and the sigma. And let's consider one with a mu of -1 and a sigma of 0.8. And if you have a look at the actual probability distribution function, you can see that it starts around 0, and I cut it off at around 2. And what I have done here in this plot is I drew a line over the expected value for this distribution. Okay? And what you might see already is that this is around somewhere around 0.4, while our parameter mu is around -1. Okay? So why? And the reason for this is that these two parameters are actually not the parameters are actually not the moments of the log normal distribution, but those are actually the moments of the underlying normal distribution. Okay? But we still modeled those terms. So any predicted parameters that we achieve have to still be transformed to the expectation or the variance of y, right? And so what essentially happens often is that you are at an output of some model. So let's say this is a Gamos type model. This plot is sliced in two parts. So we have here the results for the first parameter, which is the mu. And it has an identity link function, and then we go to the second parameter, the sigma, which has a log link function because it only can be positive. And so what you see here is we have some results for those two for those two terms. This is just some general data that I simulated, and this is a penalized spline here, and we model this penalized spline, and we get results for that. Okay, and so you look at that, and what happens is that you're really confused, right? Because what do those splines actually mean? How does this relate to the moments? And actually, how does my link function take part in this? And so what happens is that we're confused, right? And so this is solved by my package. And so there is a package needed which helps users view and compare the complete predicted distributions without studying 5 years of statistics and without being the greatest R freak, and also to make the interpretation of the covariate effects easier so that we can actually see how the location and the variance of our distribution changes over those variables. And for that reason, the District.vis was born, which was first only worked with the bamlss package. That's why it was called bamlss.vis. So I got you really excited now about my package. So let's talk about it. So of course, it is an R package. That's why you're all here. And it seeks to achieve the following two goals. And that was what I tried to code throughout the whole package, that it only is about those two goals. To see and compare the expected distribution for a chosen set of covariates, and also to view the direct relationship between moments of the response and a chosen explanatory variable. And at best, it should be interactive. So that's what I wanted to do. And so we have two core functions, which are called plot dist and plot moments. And we can use those functions with both the Gamos and the bamlss class, but you already need a fitted model to be able to use this package. So let's look very shortly at some code for preparation. We have a wage model here, so a model for modeling wage, basically. So we have a Gamos here. We use the log normal distribution and some parameters here, And we now have like 4 or 5 different scenarios which we predicted. And we have now these 5 different predicted parameters. And we now want to see, okay, so we see these values, but how does the distribution actually look different? And then we used the plot dist function with those predicted parameters. And what comes out is essentially this. So we have our variable of interest, the one we model on the x-axis, and the density of those distributions on the y-axis. And so we can really see, based on those 5 scenarios that we selected, we can really see what the difference is between those distributions. And furthermore, we can also do that. We can also see an influence plot. So when we use the plot moments function and use a selected variable, which is, for example, called age, and we can now see the influence of this variable age here on the bottom on the 2 moments of the distribution. So these 2 parts are the first 2 moments. Ex stands for the expectation, and Vx stands for the variance. And we see, based on those 5 different scenarios, we see what the influence of our age on the predicted distribution is. Okay, so that was that. And so we have the right functions to help interpret distribution regression models. But users might have a hard time remembering the correct functions. I mean, you know how it is. There's so many packages. Nobody really remembers all the different functions and their arguments. And also, some users might want to quickly compare different prediction scenarios. So we want to do this in kind of an interactive way, which is the perfect use case for the Shiny framework. So another Shiny app. And so have a look at how it actually looks like. If you're not an RStudio guy or lady, you can actually use this code right here, district.vis, vis, and that calls the app. Or we can also call it with the add-ins button on RStudio. And so what happens then is a window pops up, and we now have a layout which looks like this. And we can now go ahead and select a certain model. So I go here and I select some wage model that I just fit. And it shows me the family, which I predicted, and some formulas for the mu and the sigma in that. So some general overview about the function, the model, so that we don't get lost. And then I can go ahead and go to the next tab. And what happens here is that we have a new window with basically all the variables that I used to estimate the model. So we have age here, race, year, and education, for example. And now we can just select some scenario and see how the distribution actually looks like, the predicted distribution. So let's do that. Oops, that's the last slide. So let's go ahead and just create a scenario. We just click on Create Scenario. We select some covariates here. And now we see what the predicted distribution actually looks like, which is pretty cool. But actually, the real power comes in when we compare different scenarios that we selected here. And that's what I'm going to do next. So I'm varying the education around here and create a new scenario for every different education level. And that's the result. Okay? So for a 42-year-old person who's white and lives in the year 2006 and has those different education levels, we can see what the predicted distribution would actually look like. And that helps users get a more sense of what they're actually doing, what they're actually modeling, right? And of course, we can also see the cumulative distribution function, and we can also select some color palettes, which I can show you in the next slide. So you might have, for example, heard about the Viridis color palette, which is my favorite color palette, because it actually is really beautiful and it takes care of color blindness. And so you can select it. And if you're a scientist or researcher and you have spent some minutes figuring out how everything works, and then you want to actually obtain the code that you used to make these plots, you can actually just press on a button, obtain code, and now you get your R code to reproduce this plot so that you can just copy and paste it and make a new one, and then it's publication ready, basically. Okay, so what if you want to play around with your data? You don't want to use all those sliders. I have a solution for you as well. You go to the next tab, and here you see basically all your data that you actually input, and you can just select some cells or give your predictions some names, so prediction 1 or prediction 2 or stuff like that, and then it comes up here. So that works as well. And then, of course, we also want to view the influence of one variable on our moments. And for that, you can just head to the Properties tab, and then you actually see the influence of one of your variables, which you selected on the right, on those two moments. And this is, of course, depending on all the scenarios that you put in on the left. So this depends on how you selected your data. Yeah, so you can obtain the code for this plot as well. And then if you're done, you can close the app. Okay, so that was a short showcase of my application. So what is yet to come? I wanted to support both the GAMLs and the bamlss objects. This I achieved around 2 weeks ago, hence the name change. And also I want to involve a lot of people who do distributional regression and see how they, what their experiences with this app is. And also I want to support all GAMLs pointdist families because, I mean, if you have worked with GAMLs before, you know that there are like 150 different distributions. I want to support all of them, which is not working at the moment. And also I want to be able to support more effects. So for example, I could imagine having like a card where you select, when you have a spatial term, you select some point and then it gives you a distribution for exactly this point. And also I want to support your own function that depends on those parameters. So you might have some Gini coefficient or some other measure that depends on your distribution. I want to be able for you to upload this and then see what the results would be with this kind of measure as well. And also multivariate distributions are coming, so that's cool. And in the end, I want to admit to Quran. This will happen sometime in the fall, I guess, and I will submit it to the Journal of Statistical Software. Yeah, so if I got you really excited now, you can see my code and the guide at my GitHub page, which is around here. And also my presentation can also be found, so if you want to go through the slides in a little bit more time, you can do that as well. Yeah. So that was that, and I thank you all for your attention.
So, time for a quick question. Anybody got a question? Okay, yeah, down to it now.
Thank you. Yeah, thanks for your talk. Are your functions able to deal with interactions in the models? Because I can imagine that then the plots get complicated.
Yes, they are. So this basically only depends on the data you used to make your models. But what you actually did with those, what effects you modeled, random effects, splines, whatever, this doesn't matter. So you can use it. Just works with all the data you provided. So whatever you did with it, it will work.